The Pearson correlation coefficient, usually denoted by R, measures how strongly two quantitative variables move together in a straight line linear way. Imagine you are watching two friends walk side by side on a road. If they always keep the same distance, you would say they have a strong positive relationship. When one steps forward, the other does too. If one steps forward while the other steps back, the relationship is negative. If they wander independently, there is no relationship. Numerically, R is a single number between -1 and +1. R equals +1 perfect positive linear relationship. All points lie exactly on an upward sloping line. R equals -1 perfect negative linear relationship. All points lie exactly on a downward sloping line. R equals 0, no linear relationship points are scattered randomly. The magnitude R tells how tightly the points cluster around a straight line, while the sign tells the direction of the association. The coefficient is called Pearson because it was introduced by Carl Pearson in the early 1900s, and it assumes the relationship is linear, and the data are measured on interval or ratio scales. Explanation: the formula for R comes from two earlier concepts: covariance, a measure of how two variables vary together, and standard deviation, a measure of how a single variable varies on its own. Covariance of x and y is cov of x and y equals 1 over n sum from I equals 1 to n of x sub I minus x bar times y sub I minus y bar. It is positive when high values of x tend to occur with high values of y, negative when high x pairs with low y, and 0 when the variables vary independently. Standard deviations are s sub x equals the square root of 1 over n sum from I equals 1 to n of x sub I minus x bar squared. S sub y equals the square root of 1 over n sum from I equals 1 to n of y sub I minus y bar squared. The Pearson correlation normalizes covariance by the product of the two standard deviations. R equals cov of x and y divided by s sub x times s sub y, which equals the sum from I equals 1 to n of x sub I minus x bar times y sub I minus y bar divided by the square root of sum from I equals 1 to n of x sub I minus x bar squared times the square root of sum from I equals 1 to n of y sub I minus y bar squared. By dividing by the spread of each variable, R becomes a unit-free measure that always stays in the interval -1 to 1, regardless of the original units of x and y. This derivation shows that correlation is simply a scaled covariance, turning an absolute joint variation into a relative comparable index. Explanation: let us compute R for a small data set of 5 paired observations. Suppose we measure the temperature degrees Celsius in a workshop X and the amount of metal expansion millimeters Y. I1 x20 y 0.5, I2 x25 y 0.65, I3 x30 y 0.8, I4 x35 y 0.95, I5 x40 y 1.10. Step 1 - find means. X bar equals open parenthesis 20 plus 25 plus 30 plus 35 plus 40 close parenthesis divided by 5 equals 30. Y bar equals open parenthesis 0.50 plus 0.65 plus 0.80 plus 0.95 plus 1.10 close parenthesis divided by 5 equals 0.8. Step 2 - compute deviations and products. Create a table of xi minus x bar, yi minus y bar, their squares, and their product. I1 xi minus x bar equals -10, yi minus y bar equals -0.3, product equals 3.0, x deviation squared equals 100, y deviation squared equals 0.09. I2 xi minus x bar equals -5, yi minus y bar equals -0.15, product equals 0.75, x deviation squared equals 25, y deviation squared equals 0.0225. I3 xi minus x bar equals 0, yi minus y bar equals 0.00, product equals 0.00, x deviation squared equals 0, y deviation squared equals 0. I4 xi minus x bar equals 5, yi minus y bar equals 0.15, product equals 0.75, x deviation squared equals 25, y deviation squared equals 0.0225. I5 xi minus x bar equals 10, yi minus y bar equals 0.3, product equals 3.0, x deviation squared equals 100, y deviation squared equals 0.09. Step 3 - sum the columns. The sum of open parenthesis xi minus x bar close parenthesis times open parenthesis yi minus y bar close parenthesis equals 3.00 plus 0.75 plus 0 plus 0.75 plus 3.00 equals 7.50. The sum of open parenthesis xi minus x bar close parenthesis squared equals 100 plus 25 plus 0 plus 25 plus 100 equals 250. The sum of open parenthesis yi minus y bar close parenthesis squared equals 0.09 plus 0.0225 plus 0 plus 0.0225 plus 0.09 equals 0.225. Step 4 – plug into the formula. R equals 7.50 divided by the square root of 250 times the square root of 0.225 equals 7.50 divided by 15.81 times 0.474 equals 7.50 divided by 7.50 equals 1.00. Thus the data show a perfect positive linear relationship, as expected because the numbers were generated from a straight line. In a real-world problem you would rarely get exactly one, but the steps remain the same. Key practical tip: use a spreadsheet or calculator to avoid arithmetic mistakes. The formula works for any sample size n greater than or equal to 2. The Pearson correlation R has several important properties. 1. Range: mathematically, -1 less than or equal to R less than or equal to 1. The extremes happen only when all points lie exactly on a straight line. 2. Symmetry: swapping x and y does not change R. R sub xy equals R sub yx. 3. Unit free: because we divide by the standard deviations. The value does not depend on the units of measurement, degrees Celsius, meters, dollars, etc. 4. Linear only: R captures only linear association. Two variables may have a strong curved non-linear relationship and still produce a small absolute R. Classification of strength: rules of thumb, not strict laws. 0.00 to 0.10, negligible or no correlation. 0.10 to 0.30, weak. 0.30 to 0.50, moderate. 0.50 to 0.70, strong. 0.70 to 0.90, very strong. 0.90 to 1.00, extremely strong. Sign tells direction. Positive: plus when x increases, y tends to increase, for example engine speed versus fuel consumption. Negative: minus when x increases, y tends to decrease, for example speed of a car versus travel time. 0. No linear trend, for example shoe size versus IQ. Remember that a correlation of 0 does not prove independence. There could be a hidden non-linear pattern. These classifications help engineers decide whether a linear model is appropriate for design, control, or prediction tasks. When we calculate a sample correlation R, we usually want to know whether the observed value could have arisen just by random chance, if in the underlying population the true correlation were 0. This is a hypothesis testing problem. Null hypothesis H0 rho equals 0, no linear correlation in the population. Alternative hypothesis, H1 rho not equals 0, two-tailed test, or rho greater than 0, rho less than 0 for one-tailed tests. For a sample of size n, the test statistic follows a t-distribution with degrees of freedom n-2t equals r times square root of n-2 divided by square root of 1 minus r squared. The steps to perform the test. Compute r from the data. Calculate t using the formula above. Look up the critical value t alpha over 2 n-2 from a t-table for a chosen significance level alpha, for example 0.05. Decision rule: if absolute value of t is greater than critical value, reject H0. The correlation is statistically significant, otherwise fail to reject H0. Example: suppose n equals 12 and r equals 0.55. T equals r times square root of 10 divided by square root of 1 minus r squared equals 2.08. With degrees of freedom 10, the two-tailed critical value at alpha equals 0.05 is about 2.228. Since 2.08 is less than 2.228, we do not reject H0. The evidence is not strong enough to claim a real linear relationship at the 5% level. P-value approach: compute the probability of obtaining an absolute t as extreme as observed. Many calculators give this directly. The t-test assumes the data come from a bivariate normal distribution in engineering practice with moderate sample sizes, and no extreme outliers. The test is robust enough. Finally, remember that statistical significance does not imply practical importance. A tiny correlation can be significant with a huge sample, yet be useless for design. Key takeaway: use the t-test, or p-value, to decide if the observed correlation likely reflects a real linear link, not just random fluctuation. Explanation: a scatter plot is a simple graph that shows each paired observation as a point in a two-dimensional plane. It is the visual partner of the correlation coefficient. The steps to construct one. Step 1. Choose axes. Put the independent variable, the one you think causes or explains, on the horizontal x-axis and the dependent variable on the vertical y-axis. Step 2. Select scales. Look at the range of each variable. Pick equally spaced tick marks that cover the whole range, leaving a little margin on each side so points are not stuck to the border. For engineering data, you often use a linear scale. If values vary over orders of magnitude, a logarithmic scale may be better. Step 3. Label axes. Write the variable name and its units, for example temperature degrees Celsius, under each axis. Include a short title that describes what is being plotted. Step 4. Plot points. For each observation x sub I, y sub I, locate the corresponding x-coordinate on the horizontal axis and the y-coordinate on the vertical axis, then mark a small dot or circle. If the dataset is large, use a light semi-transparent marker so overlapping points become darker. Step 5. Add a trend line optional. Drawing the least squares regression line helps viewers see the overall direction. Step 6. Check readability. Make sure tick labels are not cramped and the plot size is large enough for detail. Practical analogy. Think of a scatter plot as a map of friendships where each person is placed according to two attributes: height and shoe size. By looking at the cloud of dots, you can instantly see whether taller people tend to wear larger shoes, positive slope, whether there is no pattern, random cloud, or whether the relationship bends, curved cloud. A well-made scatter plot instantly tells you the shape of the relationship, any clusters, and any outliers that may influence the correlation. When you look at a scatter plot, you are reading the story that the raw numbers are telling. Different visual patterns correspond to different numerical behaviors of the correlation coefficient. Tight linear upward trend points tightly clustered around an increasing straight line, are close to +1, strong positive. Tight linear downward trend points clustered around a decreasing straight line, are close to -1, strong negative. Diffuse cloud, no clear line, points scattered all over the plot, are near zero, little or no linear association. Curved, for example parabola pattern, points follow a clear curve but not a straight line. R may be moderate or even low because Pearson only captures linear trends. A non-linear transformation like squaring x could reveal a stronger correlation. Clusters, two or more groups of points separated in the plane. Overall R can be misleading. Inside each cluster the relationship may be strong, but the overall coefficient could be small because the clusters are offset. Outliers, one or a few points far from the main cloud. Outliers exert a large influence on both R and the regression line, potentially inflating or deflating the coefficient. Real-world analogy. Imagine you are watching cars on a highway. X equals speed, Y equals fuel consumption. Most cars form a smooth upward line. Higher speed leads to higher fuel use. If a heavy truck appears, an outlier that uses a lot of fuel even at low speed, the overall correlation might drop, even though the bulk of traffic follows a clear pattern. Practical tip for engineers. Always glance at the scatter plot before quoting a correlation number. If you see curvature or outliers, consider transforming variables or using a different measure of association, for example Spearman's rank correlation or a non-linear regression model. The visual pattern therefore validates or qualifies the numeric value of R. Explanation: the slope b of the ordinary least squares regression line that predicts y from x is directly linked to the Pearson correlation coefficient. Regression line y hat equals a plus bx, where b equals the sum of open parenthesis xi minus x bar close parenthesis times open parenthesis yi minus y bar close parenthesis divided by the sum of open parenthesis xi minus x bar close parenthesis squared. Notice that the numerator is the covariance and the denominator is the variance of x using the definitions of R, S sub x. and s sub y, we can rewrite the slope as b equals r times s sub y over s sub x. Derivation: step 1. Start with the covariance form of r. R equals the sum of open parenthesis xi minus x bar close parenthesis times open parenthesis yi minus y bar close parenthesis divided by open parenthesis n minus 1 close parenthesis s sub x s sub y. Step 2. Multiply both sides by open parenthesis n minus 1 close parenthesis s sub x s sub y. The sum of open parenthesis xi minus x bar close parenthesis times open parenthesis yi minus y bar close parenthesis equals r times open parenthesis n minus 1 close parenthesis s sub x s sub y. Step 3. Replace the numerator in the slope formula with this expression. And note that the sum of open parenthesis xi minus x bar close parenthesis squared equals open parenthesis n minus 1 close parenthesis s sub x squared. Then b equals r open parenthesis n minus 1 close parenthesis s sub x s sub y divided by open parenthesis n minus 1 close parenthesis s sub x squared, which simplifies to r times s sub y over s sub x. Thus, the slope is the correlation scaled by the ratio of the standard deviations. If the variables are measured in the same units, so s sub y equals s sub x, the slope equals r. Example: using the temperature expansion data from the earlier computation, we have r equals 1.00. S sub x equals the square root of 250 divided by 5, which is 7.07 degrees Celsius. S sub y equals the square root of 0.225 divided by 5, which is 0.212 millimeters. Then b equals 1.00 times 0.212 divided by 7.07, approximately 0.030 millimeters per degree Celsius. Indeed, each 1 degree Celsius rise produces about 0.030 millimeters expansion, matching the linear rule we built the data from. Why this matters to engineers: knowing r gives you a quick sense of direction and strength, while the slope tells you the rate of change, the engineering constant you need for design. Both come from the same underlying calculations, so you can compute one and instantly obtain the other. Practical note: when reporting a regression line, always give the correlation coefficient as a measure of fit quality. For example, b equals 0.030 millimeters per degree Celsius. R equals 0.98. Step 1 means x bar equals 3.0, y bar equals 4.12. Step 2, deviations and products. Observation 1. X minus x bar equals minus 1.0, y minus y bar equals minus 2.32, their product equals 2.32, x deviation squared equals 1.0, y deviation squared equals 5.3824. Observation 2. X minus x bar equals minus 5/10, y minus y bar equals minus 1.22, their product equals 0.61, x deviation squared equals 0.25, y deviation squared equals 1.4884. Observation 3. X minus x bar equals 0, y minus y bar equals minus 0.12, their product equals 0, x deviation squared equals 0, y deviation squared equals 0.0144. Observation 4. X minus x bar equals 5/10, y minus y bar equals 1.28, their product equals 0.64, x deviation squared equals 0.25, y deviation squared equals 1.6384. Observation 5. X minus x bar equals 1.0, y minus y bar equals 2.38, their product equals 2.38, x deviation squared equals 1.0, y deviation squared equals 5.6644. Step 3, sums. The sum of x minus x bar times y minus y bar equals 5.95. The sum of x minus x bar squared equals 2.5. The sum of y minus y bar squared equals 14.188. Step 4, correlation. R equals 5.95 divided by the square root of 2.5 times the square root of 14.188, which is 5.95 over 1.581 times 3.769, approximately 5.95 over 5.96, giving about 0.998. Step 5, scatter plot description. The x-axis is pipe diameter in centimeters ranging from 1.5 to 4.5. The y-axis is flow rate in liters per second ranging from 1.5 to 7.0. The 5 points lie nearly on a straight line that rises from the lower left to the upper right. Adding the regression line would pass almost through every point. Step 6, significance test. Sample size n equals 5. Compute t as r times the square root of n minus 2 divided by the square root of 1 minus r squared. Plugging in the numbers gives 27.5. Degrees of freedom equals 3. The critical t for alpha 0.052 tailed is about 3.182. Since 27.5 is much greater than 3.182, we reject the null hypothesis and conclude the correlation is statistically significant. Final comment: the data show a practically perfect positive linear link between pipe diameter and flow rate. A larger pipe carries substantially more water. Both the numeric coefficient, r approximately 0.998, and the visual scatter plot confirm this, and the hypothesis test tells us the observed relationship is not a chance occurrence. Takeaway for the exam: follow the ordered steps, compute means, deviations, sums, r, draw the plot, then perform the t-test. Present the conclusion clearly: strong positive, statistically significant, p less than 0.01.